Have you ever wondered how crude oil becomes fuel for your car or gas for your kitchen? Well, what if I told you we built a simulator that does exactly that right on a computer? My name is Prince and I'm here with my colleague Izo. Together we built PETROSIM, a crude oil distillation simulator based on Ghana's Summer Oil Refinery. And today we are breaking it down in the simplest way possible. I'll walk you through the big picture and Izo will take you behind the scenes into the codes. So here's the big idea. Crude oil is a mixture of different substances, each with its own boiling point. When you heat it, the lighter components rise, the heavier ones stay at the bottom, and the distillation column separates them step by step. But we didn't just study it, we simulated it. So how does a computer actually model something like this, Izo?
Alright, so behind our program PETROSIM is a MATLAB code that models what happens inside the column. First, we calculate K values, which are the equilibrium, using thermodynamics equations. These tell us whether each component prefer to be vapor or liquid. We then use the Rashford-Rice equation to determine how much of the mixture becomes vapor on each tray. Then we simulate column tray by tray vapor to see whether vapor moves up or liquid flows down until the system stabilizes. We've also included tray efficiency, calculated using the Murphy tray efficiency equation to reflect real-life conditions since industrial equipment isn't perfect. And finally, this program generates graphs showing temperature, composition, and energy usage across the column. So as you can see on your screen right now, all this is the code that we wrote for our program PETROSIM to show us the graph and to visualize how it goes on in an actual refinery. So in order to call this, we first have to call the function or the program that we type, which is PETROSIM. So I have PETROSIM here, and once I press enter, you can see on your bottom left corner that is busy. MATLAB is bringing it up. Perfect. So as you can see, the first thing at the top left corner, you can see Jubilee crude into bracket Ghana. This is simply the crude type we are using. We've done our model in such a way that the crude type can be changed, but the default one is Jubilee crude because that is what is used in thermal oil refining. You can also change it to the Bonga crude, which is used in Nigeria. So if our model were to change to illustrate the Dangote refinery, the Bonga crude could be used. Then we also have the number of trays. Okay, the number of trays is simply the number of trays inside the column. Then we have the reflux ratio, which is the ratio of the liquid that is sent back to the product that is gotten. Sometimes in the refinery, the higher yields, those got at the top, those of lighter temperature, sometimes they may be sent down to get more heat in order to separate further. Then we have the tray efficiency, we have the feed rate, which is simply our amount. Now the maximum here is 45,000 because that is the maximum capacity at thermal oil refinery. But if this model were to illustrate the Dangote's oil refinery, which produces about 700,000 barrels, that's what we have. We also have the crude price, okay, which is in dollars because internationally the price of crude is always recognized in dollars. So because of that, we've included a converter here, which is for the exchange rate. So if the exchange rate is 14, you put it there. If it is 11, you put it there. So let's say the exchange rate is 16 right now, so we'll leave it there. And let me reduce the price of crude to, let's say, $55 a barrel. Okay, let's leave it at 58. Then let's run it and see what is going to happen. So as you can see, MATLAB is running the code right now. So the first graph you had at the top left side, this is the temperature profile, and this is basically telling you the temperature at which each tray is at. So if a tray is at, every component in the crude has where it separates. For petrol, you can expect petrol and other light gases at around -125, and the residue at temperatures above 500. Okay, so this graph is simply telling you what temperatures you expect at what trays. And then you have the second one, the very colorful and very wide one. Okay, it's telling you also what components you expect at the various trays. Okay, this is more detailed. So they are telling you from tray 1 to around tray 4, you should expect light gases, as you can see on the color code. Okay, and above tray 20s, you can expect the residues there. Then we have the third one, which is the vapor fraction per tray. This telling you the amount of vapor to expect on each tray. Then we have the component distribution. This, engineers love graphs. This help us to track each component throughout the distillation column. So if I take light gases, which is the blue dash here, I can track it to see each amount in the various trays. You can see by tray 10, as it starts to get very hot, no petrol will be found there. So as you can see, the light gases there is almost zero. Okay, and the residue, which are very high temperatures, can be found in large quantities around the higher trays, which is from tray 20s onwards. Okay, and now the last one, this is heat usage per tray. This simply helps engineers to know how much energy they are using per tray in the refinery, so that they can know the total energy they are using in the refinery. Then when we go to yield summary, very important, this tells us how much of each component we are actually producing and the prices at market value, so that we can know our total revenue. So in order to maximize profit, we have to reduce the amount of residue we are producing, because residue is not as valuable. That means increasing efficiency.
Yeah, so basically we built a digital refinery. Not just digital, a simplified version that is powerful enough to analyze real processes. And here's where things get interesting. We didn't just simulate the science, we added the business side to it. The simulator calculates revenue from refined products, cost of crude oil, energy and operating costs, and then gives us the profit per day. But here's the twist. If you increase efficiency, energy costs go up. If you reduce energy, separation becomes poor. So the real question is, where is the balance? For our system, the sweet spot is a reflux ratio of about 2.5 to 3. At that point, the refinery can make around $270,000 per day. So yeah, that's PETROSIM in action.
Thank you very much for your attention.
Unless I forget, before we wrap up, it doesn't just show how engineering code. This project just shows how engineering, coding, and economics all come together to solve real world problems. And that's the story, from equations to code to real impact. Thank you very much.